The next talk is entitled Attention-Based Optimization for 3D Shape Registration. And the authors are Alessandro Riva, Lorenzo Olearo, and Simone Melzi, all three from University of Milano Bicocca in Italy. And Alessandro will give the talk.
Hello everyone, I'm Alessandro, I work in Milano, and today I am here to present you our latest work with transformers and in particular attention for shape registration. Let's start with a little introduction about shape registration, which is something I think you're all pretty familiar with, but let's give a little notational details. So we will call our source mesh B and our target mesh A, and what we want to do is compute a transformation that maps the points of B over the shape of A. In the discrete setting of meshes, this can be done by computing a permutation of the points of A, rather a soft permutation, so it's a linear combination of the points of A. So what we have is this, we want to compute this pi matrix that we call pi BA. And that's all for shape registration. Now, what is attention, which is something maybe we are not all so familiar with? It's a function that is a sequence-to-sequence function that takes as input a sequence of tokens. In our case, we'll talk about points as tokens, and outputs a fourth sequence of a third sequence of tokens. And we see that we have the first sequence, that's A, that we call the context sequence, that is mapped into two different spaces that are the value space and the keys space. And then we have the second sequence, B, that is our input sequence, that is mapped in a space that we call Q. Now, V, K, and Q are values, keys, and queries, based on the idea that you have a query and you want to recover some information that is mapped in the keys, and the output will be a product of the values. For our work, we focus mainly on the row and pi matrices that we have here, and those are the correlation matrix between K and Q, and the softmax version of the correlation matrix. So what we have here is that we have this pi matrix that has the same shape of the type of registration that we want to compute, and is, in a sense, a linear combination of the points of A. Is actually generally used as a linear combination of a projection of the points of A, but for our scope, we say that it's a combination of the points of A. Now, before we look at what we've done, a little bit more of notation on attention. We call self-attention and attention functions that receives as input the same sequence twice. So you are computing relationships inside the same sequence. And we call cross-attention an attention that receives two distinct sequences. So our work stems from this similarity between the representation of a shape registration matrix, so a soft permutation matrix, and the attention weights matrix. These are both point-to-point information. These are point-to-point matrices that express some relationship between points. And what we wanted to do was train a transformer, or rather optimize a transformer, because we do not training, we don't use any data, so any additional data. So we optimize a transformer so that the attention matrix represents the registration soft permutation. So this is our full pipeline, and now we'll look into details about each little step. So we have the input, which is, of course, the two meshes. It's a single couple of shapes, and each vertex is annotated with some input features. we tested the model with distance from landmarks and coordinates, which is a typical framework that is used in registration. And we also tested with diff3f, which is a learned descriptor that is based on diffusion models. At every iteration of the optimization, however, we do some resampling of the surface. And this is meant to inform the model that it's dealing with a surface rather than a set of points. The first step in our pipeline is then the self-attention transformer, and this is the same module which is applied twice. So we have the same feature extractor that looks at each shape separately and extracts a sequence of features. Now, the initialization for this module is performed by optimizing to solve the registration of the first shape with a rotated version of the first shape, and of the second shape with a rotated version of the second shape. And this is to introduce some sense of intrinsic features, because we are dealing with coordinates in 3D space, and we don't want the network to use those features as descriptors, but rather to use those information to understand what is its neighborhood. The second step of our pipeline is the cross-attention transformer, which is, again, the same module applied twice, but in one step we do with A as the context, so as the context shape, and another step it's B that is the context shape, which is very simply a way of doing a bidirectional solution, because cross-attention is not symmetric, so we want to solve for both the directions of the registration, and to do so we simply apply the same model twice. The outputs that we took out the last layer of the transformer is not the output of the attention, however. We simply cut off the last part of the attention function and we take the raw matrices. These are the correlation matrices. We sum them. Of course, one of them has to be transposed. We sum them, and later we apply the softmax in the two different directions. So we have a single correlation matrix, but we compute two distinct solutions. In doing so, we obtain the registration for the first shape and the second shape. So we have a method that is completely symmetrical and solves the registration without doing any training. So we do not need any additional data, and this is something that transformers are not usually used for. So I think it's important to stress this. The implementation of the transformer is the standard transformer that was presented in the seminal paper Attention is All You Need, with the difference that we do not use any positional encoding. And this is due to the fact that meshes and point clouds do not have any clear order of points. And the attention itself is, by definition, permutation equivariant. And this seems to fit very well the idea of operations on points. So we decided to simply not introduce any positional encoding. As a result of our sampling during the input, we obtain a solution that is also discretization invariant. So we can look here at some results. On the left, you can see some examples on very common data sets. And our method seemed to produce smoother results in most cases. And what you see, for example, on the kid in the last row, that there are some triangles that connect the the right hand of the kid with the left foot of the kid. It's actually due to the topological error that is present in the source shape. So what we do is we're plotting the registration as we're just moving the points of the mesh, and we're not changing the connectivity of the mesh. So what we're seeing is actually the first box on top is the topological error where we have the hand that is connected with some edges to the fit. So when you plot the registration, you still have the faces in the images that we see. So the error is maybe not large, but seeing it, it seems like there is some larger error. On the right, we can see how our method can be applied to many different classes of shapes, as it is not trained on any particular dataset. So what we get is that if you have enough landmarks or enough informative features on the points, you get a good registration. We pushed our model a bit further with some tricks in the use of the attention to deal with larger meshes. Now, attention requires you to have n by n metrics if you're dealing with large meshes, and this means that we would need 2 million points by 2 million points, and a matrix that big is not something that is actually very feasible. So we were able to apply some remeshing techniques to reduce the number of vertices, and at each iteration, even if we have a higher number of vertices, we can resample the shape, and doing the resampling in the input, even if we have maybe 10,000 points, we resample only 1,000 points. We do at each iteration this resampling, and in the end we obtain a network that is able to recover the whole mesh without having seen it in its entirety. Never. We see on the left, on the right, we see on the right the results of a segmentation transfer. Now, it is to notice that some of the bones in the camellia, for example, don't appear on the turtle, being the camellia on top and the turtle on the bottom. And for example, in the casque, you can see that there are some bones that are not present in the turtle, but are mapped in a reasonable position. This is kind of it. I don't think it's interesting to go over too many numerical results. So if you have any questions, I'm open for it. The code for all this is available. It has undergone some major refactoring recently due to some difficulties with compatibility. So if you have any issues and you want to use it and it doesn't work, please open an issue or send me an email and I will happily help you out. Yeah.
Thank you, Alessandro. Are there questions for our speaker? We have one question here.
Thanks for. Can you hear me? Thanks for the nice talk. I was wondering, since the input to your method is essentially the two sampled point clouds from each shape, did you investigate if like sampling differently or non-uniformly on your shapes has any impact on the correlations that the attention kind of produces from the points?
Sorry, I didn't quite catch that.
Does the sampling on the two shapes has an impact on the kind of correlation between the two shapes?
Yes. What we do is we actually perform a random sampling on the surface in a very naive way. And I think it's a place where we can actually improve the method. It is, I think, problematic because if you have a shape that is uniform in area, maybe, so you have all the faces that are mainly the same shape, the same size, you don't have problems because you're sampling enough times to cover the whole surface. but in the moment that you have different densities of points, it can become problematic, yes.
Just to kind of to understand this a bit more, do you have any intuitions on how the attention deals with this kind of like disparity in locality when it comes to the sampling, or?
I think that as you're dealing with registration, as much as there is disparity in both surfaces, you don't kind of get any big effect. But if you have a very dense area on one part of the mesh in the source, and then the target is a very dense area in another part of the mesh, I think you would get some problems, yes. You would need a better sampling strategy.
Okay, thank you.
You're welcome.
We have another question
Yeah.
from the back of the room.
So just one quick question. I was wondering, as you need to train for each shape, what is the performance of this? How much time does it take to do the shape matching for one
It takes
example?
quite a bit. It takes like 3 or 4 minutes for a couple, which is quite a lot, of course. It is also a very naive implementation of transformers. I think it can be improved greatly with some more work on it, yeah.
Okay, thank you.
One question really from the back of the room this time.
Yeah, so I was wondering, since you have the self-attention, right, on each shape, if that could be used to correct the topological errors, because you'd see that things are connected in one versus the other, and then the discrepancy after registration between the self-attention would show you that the mesh should be updated there, right?
We worked only on registration without dealing with connectivity, but I am actually of the idea that this type of application could be used to solve some connectivity issues. Maybe even something like predicting connectivity of points. I think this is something that could be used for that, but we never did any experiment. But I think it's an interesting direction to go.
Thank you.
Thank you.
Okay, if there are no more questions, let us thank one more time Alessandro